Alright, for this lecture, we're going to go over Chapter 10. Again, this is a review over VSEPR and formal charges. Let's get started. Let's first start with an example. Xenon difluoride. First thing we're going to do is make a rough draw of xenon difluoride. So we know xenon's going to be central because it's more electric positive, while your fluorines are the most electric negative. Alright, so here's my rough draw. Second thing we're going to do is we're going to count our electrons. Xenon has 8 valence electrons, while fluorine has 7 valence electrons times 2 gives us 14, and when we add that up, we get 22 valence electrons. Next, we're going to draw what we know. So right now we have 2 single bonds. So that means we take out 4 electrons, because we know that one single bond is actually 2 electrons. So that gives us 18 electrons left over. Or it can be 9 lone pairs. So let's add in those lone pairs. Let's see if we can fill this up. So we know fluorine has 3 lone pairs each. So that gives us 6. And xenon, well, maybe we could put those 3 extra lone pairs on the xenon. So let's check our formal charges. Well, how do we check formal charges? Well, first, we need to know what the definition is. So formal charges are mentally splitting each bond pair in half and credit 1 electron to each atom in bonds. So the formula is formal charges equal the number of valence electrons minus the number of electrons on the atom of the structure. So let's take a look back. So fluorine needs to have 7 valence electrons, and we have 3 lone pairs, so that gives us 6 plus 1 from that single bond. So that gives us 7 electrons. So it has a formal charge of 0. Because the fluorine on the right-hand side has the same structure, we know it has a formal charge of 0. Now let's take a look at xenon. So we know xenon has 8 valence electrons, and it has 2 electrons coming from the single bonds, and it has 3 lone pairs, so it gives us a total of 8 electrons. So it too has a formal charge of 0. This is perfect because we notice there is no charge for xenon difluoride, so having 0 formal charge works. Now the next step is we need to figure out, well, what is this angle? What is its VSEPR? So we're going to look at the central atom, xenon, and we're going to count how many things are around xenon. So we're going to take our little red marker. We have 1 lone pair, 2 lone pairs, 3 lone pairs, 1 single bond, 2 single bonds. So that gives us 1, 2, 3, 4, 5 things around it. So if you remember from last lecture, something that has 5 electron groups around it was known as a trigonal bipyramidal. And we know it has a structure that looks like this, where it has 3 lines, 1 wedge, and 1 broken wedge. So let's draw xenon difluoride as a VSEPR. So we're going to have xenon in the middle. We're going to draw out a trigonal bipyramidal. Now, one thing that's unique about trigonal bipyramidals is that the lone pairs have to be on the equatorial. So if you remember, our equatorials is this line here and our wedges. Our axials are these lines right here. So let's draw our lone pairs on the equatorial. Next, I'm going to draw in my fluorines. So now I have my picture. So just to remember, your angle right here is a 120 angle. Your angle right here is at 90 degrees. And these fluorines are at 180 degrees. This is actually a linear molecule, but for this course, it's going to be a trigonal bipyramidal, sorry, because that's what we're going to be focusing on for this course. So let's do another example. So let's look at phosphate, PO4 3-. So the first thing we're going to do is just do a rough draw. So we know our phosphorus is in the middle because it's more electric positive. And I'm going to draw my oxygens around it. Now we're going to count our electrons. Phosphorus has 5 valence electrons. Oxygen has 6 valence electrons times 4 gives us 24 electrons, which gives us right now 29 electrons. But don't forget, we need to add in the charge, so we're going to add in 3 more electrons to give us 32 electrons. Now let's draw what we know. So right now we know we have 4 single bonds. So we're going to take out 8 electrons, giving us 24 electrons, or 12 electron pairs or lone pairs. So let's draw in our lone pairs. So we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 lone pairs. Now let's do the let's do the formal charges. So we know oxygen needs 6. I have 1, 2, 3 lone pairs, so that's 6, plus 1 electron from the double bond, which gives me 7. So it has a formal charge of -1. Well, if I look at all of these oxygens, they are exactly the same formal charge as this oxygen. So I'm going to put the charge on the oxygens. Now let's take a look at phosphorus. Phosphorus needs 5 valence electrons, but I have 1, 2, 3, 4, which gives me a +1 charge. Now this does give me phosphate, but there's a lot of formal charges. So this wouldn't be the best resonance structure. So let's try building this up again. And this time let's add a double bond so we make phosphorus a 0 formal charge. Now we had 24 electrons left over, but now because we added this double bond, we're going to take out 1 more lone pair to give us 22 electrons. So let's add these electrons in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this gives us 11 lone pairs, which works. So now let's check our formal charges. So oxygen, again, needs 6 valence electrons, but this oxygen here has 7, so it gives us a -1 charge. This oxygen and this oxygen is similar in structure as this oxygen, so they also have a -1 charge. But this oxygen here has a different structure due to the double bond. So let's count how many, what its formal charge is. So we need 6 for oxygen, and we have 1, 2, 3, 4, 5, 6. So it gives us a formal charge of 0. Now let's take a look at phosphorus. Phosphorus needs 5 valence electrons, and we have 2, 3, 4, 5. So it also has a formal charge of 0. Now if you remember what is the best resonance structure, the best resonance structure is going to be one with the least amount of formal charges. So because we only needed a 3- or 3 formal charges, that's going to be the best one instead of the last figure where there's 5 formal charges. Alright, so let's draw the VSEPR. So again, we're going to look at the central atom, and we're going to count how many electron groups are around there. So we have 1 double bond, 1, 2, 3 single bonds. So it gives us 1, 2, 3, 4 electron groups around it. So we know that 4 electron groups is known as a tetrahedral. And a tetrahedral does have a 3D shape, which looks like this, where it has 2 single lines, 1 wedge, and 1 broken wedge. So let's draw our phosphate. So I'm going to put our first oxygen, the double bond, on top, then our other oxygens on the bottom, giving us this classic tetrahedral shape. Alright, so what do we know about tetrahedrals? Well, we know that they have an angle of 109.5 degrees. Earlier we were talking about resonance structures, so let's again talk about resonance structures for phosphate. So again, what is a resonance structure? So we know a resonance structure has the same connectivity between atoms. The single and sigma bonds are the same, but it's the lone pairs and double bonds / pi bonds are different. So again, let's draw all the resonance structures of phosphate. Alright, so here we have 5 resonance structures. Now, this resonance structure is non-equivalent resonance structure because it's not the same number and or bonds of lone pairs. We're missing that double bond. While these structures right here, 2, 3, and 4, these are going to be completely equivalent resonance structures. Because they are same in everything except for where the double bond is located. So let's draw some more examples, but this time I'm going to skip through the Lewis structure phase. I'm just going to draw it, so I'm not going to count the valence electrons or the formal charges, and then we're going to just start identifying the VSEPR. So let's start with xenon tetrafluoride. So its Lewis structure looks like this. So here's xenon tetrafluoride. It's going to have 4 fluorines and 2 lone pairs. So now I'm going to identify the electron group number. So here I have 4 single bonds and 2 lone pairs. So it gives me 1, 2, 3, 4, 5, 6. 6 things around it gives me the octahedral, which looks like this. So we have our central, our 2 single lines, our 2 solid wedges, and our 2 broken wedges. So let's draw out xenon tetrafluoride. Now one thing you want to keep in mind is the lone pairs need to be far apart from one another as much as you can. So when we draw out this structure, so I'm putting xenon in the middle, drawing out what the structure should look like first. The furthest angle that the lone pairs can actually be is at the 180 angle, which is right here. If you remember, these angles right here are only 90 degrees. So again, electrons need to be further apart. So whichever has the biggest angle, that's where you're going to go for. Now let's add in the fluorines. And this is our figure for xenon tetrafluoride in its Vesper form. So let's try another example. C4H10, also known as N-butane. It's what's found in lighters. First thing we're going to do is draw out its Lewis structure. Alright, so here's the Lewis structure. Now we want to identify the electron group number. So I'm going to look at the first carbon right here, and I'm going to count how many things are around it. So 1, 2, 3, 4. So my first carbon, which I'm going to call C1, has 4 things around it, which is a tetrahedral. The next carbon I'm going to look at is this carbon right here, and I'm going to count 1, 2, 3, 4 things around it. So C2 is going to be just like C1. Now let's look at this carbon, and we count 1, 2, 3, 4. So C3 is also going to be a tetrahedral shape. And our next one, this last carbon right here, 1, 2, 3, 4. So our C4 is also going to be a tetrahedral shape. So remember, tetrahedral is going to have 2 lines, a solid wedge, and a broken wedge, and everything needs to be at 109.5 degree angle. So let's draw this Vesper out. So the first thing I'm going to do is draw the hydrogen, then carbon, then go up, carbon, go down, carbon, go up, carbon, go down, hydrogen. Now the rest of the hydrogens I'm going to fill in as the wedges because I already did the solid lines for all of them. So what's left is the wedges. So I'm going to just draw in the wedges and add in the hydrogens. And this is what I get. So it's going to give me roughly that 109.5 degree angle look, which I'm looking for. Now let's try a different structure. C6H8O2. Alright, now first thing I'm going to do is draw the Lewis structure. Alright, so this is the Lewis structure I got. Now remember, I'm not going to go over Lewis structures because you learned it previously. So just do this slowly and see what you can get. Alright, so the first thing I'm going to do is I'm going to start figuring out, well, what are my electron groups for each one. So first I'm going to start with this carbon. And I notice I have 1, 2, 3, 4 things around it. So I'm going to call this C1, has 4 things around it. Next, I'm going to look at this carbon right here, and it has 1, 2 things around it. So this C2 has 2 things, so it's linear. Looking at this one right here, I count 1, 2. So C3 also has 2 things around it, so it's linear. This carbon right here has 1, 2, 3 things around it, so it is going to be trigonal planar. Now this oxygen right here has 1, 2, 3, 4 things around it, so oxygen 1 is also a tetrahedral. This oxygen right here has 3 things around it, so this O2 is going to be trigonal planar. That just means all those lone pairs are going to be in plane, but you really don't need to show them. Alright, next figure, C5, which is this one right here. I have 1, 2, 3, 4 things around it. So this is going to be tetrahedral. And then my last one right here, 1, 2, 3, 4, C6 has 4 things around it, so it's also a tetrahedral. So now we're going to start drawing this out VSEPR-wise. So here we go. And remember, it's going to take you a while to learn how to do this. So the first thing I'm going to do is I'm going to draw what I know. So I have my carbon goes to a carbon right here. Well, because this C1 is a tetrahedral, I'm going to draw the hydrogen up there and my wedges down below. So it gives me kind of that tetrahedral shape. Now this line we knew was linear from here to here, so it needs to be 180. Same with the next carbon, from here to here needs to be 180. So make sure you watch out for this. Next, we know that on this carbon we were actually at a 120, so C4 was a trigonal planar. So I'm going to draw the oxygen kind of at an angle and the oxygen down here at an angle as well. Now if we remember, this oxygen right here is at a tetrahedral shape, so that means its lone pairs are going to be wedges, and we have a line that goes this way. We know we had a carbon and another carbon that were also in tetrahedral form. So we're just going to finish drawing that out. So this is what you should get for your angles for your VSEPR. So just remember, from here to here should be about 109.5. Same with here to here to here. From this angle to this should be at 180. From here to here should also be at 180. Then this angle needs to be at 120. this angle needs to be around 120. From here to here should be at 109.5. Same with here, here, and here. As well as here, 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 and here. Here to here, here to here, here to here, and here to here. All should be at 109.5. Okay? Well, that's it for this lecture. I recommend still practicing on the PS1 handout because there's a lot more figures you can draw.